The book derives, and you can go and look at that. Length contraction comes right from time dilation. Okay, so if you take some object and you speed it up to close to the speed of light, it's not that you drag when it contracts. You don't drag the corner handle in and make it smaller. It contracts only in the direction of motion, right? So you only take the side handle. See, that's a good way to explain it, right? You know, how pictures or graphic objects get like handles around them, right? When you click on them, right? So you just drag the side handle in. And you know, there I am when I weigh a little bit less, right? Isn't it? It's sort of funny, you know. With we just got a new TV, and I'm very sensitive to the change in aspect ratio, right? Sometimes they'll mess up, like the special features on a DVD will have the wrong aspect ratio. You can tell somehow, even if you don't have like a circle that gives it away. You can just tell by looking at people and going, oh no, I don't think so, right? You know, I don't think people would look that fat, you know, side to side, right? Okay, so this is length contraction, and length contraction, the formula for length contraction is that that length equals the proper length divided by this little gamma, right? But the real formula is that L equals, right? So if you divide by the Lorentz factor is already this reciprocal thing, right? The Lorentz factor is 1 over square root of 1 minus v squared. Right? So I think the data packet makes it look, I think, a little more confusing, right? So that's the real formula. But they give it to you this way, which is kind of weird. Okay. This length contraction reconciles those frames of reference. Right? That notion of if this car is moving, right? If this guy's going 0.9 the speed of light this way, right? And then we see there the beam of light. If we see, in our frame of reference, we see the car going 9/10 the speed of light, the light going the speed of light, and the difference between their velocities is only 1/10 the speed of light. In this person's frame of reference, they see the light traveling away from them at the full speed of light, right? Okay. Well, if you take this frame of reference and you contract it, right, it's possible for this person to have a different experience than that person, yes? Yeah, I mean, it's the whole Harry Potter tent thing again, right? And then mass dilation, and this is the one that you could just read, I think if you go in your text and just read that little section on length contraction, you'll see how they derive it, okay? Mass dilation is beyond the scope of this class. But let's just imagine we've got an electron at rest, right? Have you ever wondered why they give you rest mass in energy? Isn't that a weird thing to do? Yeah? We kind of know why they do it because of this, right? Okay. But the rest mass of an electron is 500,000 electron volts, 0.511 MeV. Okay. Let's suppose we accelerate the electron through 1,000,000 volts of potential. It now has a 1 MeV of energy. Yeah? Okay. So its new mass, its dilated mass, is that 1 MeV of energy plus the half MeV of rest energy it had, or rest mass it had. Yes? So its new mass is this much. It dilates. Isn't that weird? We know this, though. Don't we know that mass becomes energy? And energy becomes mass? Yes? E equals mc squared. Okay? And so, yeah, this thing moving with that much energy, it's got to have more mass, doesn't it? Energy has to have mass, and if we talk about MeV, there it is. It's really hard. That's pretty hard to do, isn't it? Yeah. Okay. No, this is not so hard. Okay. So that's the notion, and of course, mass, since it dilates, the formula that they give you is that the dilated mass is the rest mass times that little gamma thing, right? But really, the formula is right, which I prefer, but there it is, right? So this is all you have to really remember, right? Okay. Clocks tick slower in a moving frame. Okay, moving relative to us, right? Right, in a moving frame, clocks tick slower. Length contracts, mass increases. right? For mass, it's easy, right? E equals mc squared. So if it gains energy, it gains mass, right? All right, wake up your neighbor. Let's try some of these. Mo and Joe have clocks that tick every 10 seconds. That's how long. They're really, really big clocks, right? They're 10, 5 light seconds long. You know, you can figure out how long that is, right? Okay. Joe, though, gets in his spaceship. He's flying by. He's the one flying by at 0.85 C. And so Mo is sitting still watching Joe fly by. There goes Joe. He's flying by. He's always doing that. Going a little too fast, right? And the question is, what time does Mo see Joe's clock take to tick? Notice it says trick with C. What does 0.85 C mean? Does that mean 0.85 times the speed of light? Yeah. That's not the trick, but that's what 0.85 C means. Okay. You are tempted to take this formula. This is the formula we're doing, right? And go 0.85 times 3.00. Right? You are tempted to say, I'm going to show you a better trick. To do that and get 255, right? And then just plug that in for C and then plug in C for C, yeah? Okay, but let me just show you a trick. Can I show you a trick? Because almost always in relativity problems, they'll give you factors of the speed of light because that's just what we do. We're so stylish, right? Okay, so what you can do is you can say 10 divided by the square root of 1 minus 0.85 C squared over C squared. Now, when I square 0.85 C squared, I will get 0.85 squared times C squared, won't I? Yeah? C squared over C squared is, you don't see it anymore, do you? No C. Yeah? So isn't this mathematically the same as 10 divided by square root, left parenthesis, 1 minus 0.85 squared, right parenthesis? Holy cow. That's just one trick I'm going to show you today. I have so many. Yeah, there you go. Now, supposing you only had 2 sig figs. I don't get that number. I do get that. Yeah. A dog will hunt. Ten is the proper time. That if the clock's not moving and takes place at the same place as talk, right? That's how much time it takes. That's right. That's right. Yeah. By the way, having ascertained that if we're sitting in Mo's frame of reference, we see Joe's clock take that long to tick. That's right. Rest assured that Joe, when he looks at our clock, says, "Aha! Look at their clock. Look how slow that clock's going." Joe sees our clocks ticking the same rate of speed. Because otherwise, if he saw our clocks going faster than his, wouldn't he know he's moving? That's right. And wouldn't this violate the whole? That's like, yeah. 36. What did you do when you got 36? You forgot the square root. That's right. Yeah, don't forget the square root. It would make it an infinity. And that's right. And typically what they do, and this is, IB apparently really wants you to know this because I just took the IB test. I just got done with it and I just graded it, my own test. The real limit here is this mass, right? What they want you to say, and I missed marks because I didn't say this, all I said was mass approaches infinity, but that's not enough, right? So as you approach the speed of light, your mass dilates, your mass approaches infinity, and then it takes infinite energy to accelerate an infinite mass. Right? And I forgot to say that last thing, so I missed